Good morning, students. Hopefully I think I have the microphone actually on this time, so that's nice. Hope everybody's doing okay. Today we do have quite a few things that we can go through. This was requested earlier this week because someone said, hey, we're going through new material. It's so much more helpful if you would just go over it. So I'm going to try and go over a couple of things. I will say, in my opinion, the last unit I consider to be kind of easy, but it's easy and it's weird. So Le Chatelier's principle, talking about equilibrium, it's not that difficult, but it's kind of weird. This unit actually makes sense, in my opinion. I think it makes a lot more sense. It's grounded deeply in physics, which is something I care a lot about. Chemistry's great, but physics, that's where it's at. So there will be a little bit of math this unit. Do not be concerned. It's not like mathy math, it's science math, and therefore better. So we will have a little bit of that to look forward to. So anyway, we're going to talk about heat today. All right, and I think I've fixed my tech issues that I had last Chem Chat. I think I've actually got it taken care of now, so it should work flawlessly, I hope. But let's find out. All right. Good morning, Ashley. All right, I'm gonna pop out the chat and put it over here. I'm gonna move this like that, and now I'm gonna go to desktop screen. All right. So anyway, let's see if this works. So the first thing I wrote down that I would talk about are phase curves. So I do want to talk about those briefly. So these phase diagram curves, please work. Yay, it's working. I'm so happy. Um, really sloppy drawing, but it'll still work. You have temperature that's over on this side, and we're going to go ahead and put the temperature in degrees Celsius. And down here, we can put time. That makes sense. So time as we go this way. So we got temperature, we have time. All right, now on this, okay, we're going to have a line. Now, depending which direction you're going, these phase diagrams are either going to be warming up or cooling down. And so obviously, you can look and say, oh, well, where does it start at? Does it start at a really high temperature and it's getting colder over time? Does it start at a really cold temperature and it's getting warmer over time? We don't know, but you've got to look. So obviously, this first one, then, if I start at like right here, it's going to start at a very low temperature, and as time goes on, it's going to be getting warmer. Now, when you boil water, um, you start, with just regular temperature water, but it gets warmer, 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 warmer until a certain point, and then it begins to boil. But it doesn't actually start boiling until you get bubbles, because it's actually producing water as a gas. So the phase change is when you hear that popping sound. When you boil water, you listen, you hear that popping sound. That's how you know that it's trying to change over. And so phase changes are always going to look like this. They're always going to be a flat line. Wow, what a great flat line. Let me try and do that again. Okay, that's about the same. But anyway, and so this, let's just say this is solid ice. Okay, so this is water as a solid. But when it gets to that flat line, it's actually in equilibrium with itself, because you have solid ice that you start with right here. So this is still a solid. All right, so here's our solid. But then over here on this end is when it will finally become a liquid. Okay, so we're going from solid, we're going to liquid over here. Right, I can make this so much bigger, and that would make things better. There we go. So we're going from solid ice, we're going from solid to liquid. And so in degrees Celsius, I hope that you guys know the temperature at which this occurs, okay, is going to be 0 degrees Celsius. So when you have 0 degrees Celsius, that's when the phase change actually starts to happen. And so the cool thing is, the reason I said it's at equilibrium is because both of these can exist at that temperature. It can be solid ice at 0 degrees Celsius. And again, yeah, at 0 degrees Celsius, it's also 32 degrees Fahrenheit. This is America, after all. But you can have solid and you can have liquid at the same temperature. Now, an example I like to use here is my dad actually has a refrigerator that is just his shop fridge that he got on like a Black Friday sale. And it's super, super, super cold. Like, it's colder than it should be. But the cool thing about it is you can get out a water bottle and you bang it on the ground literally you take the water bottle, you like drop it on the ground, and when you do, it instantly crystallizes into ice, which is pretty cool, literally. And it's because it's right at 32. He has his fridge set right at 32 degrees Fahrenheit. And so when you get things out, you can keep it as liquid water as long as you're careful with it. But if you put energy into it, right? If you put in energy and you bang it against something, it forms solid. It forms a solid. So it actually does crystallize. So it's pretty neat. So on this phase change, though, as you can see, there is no temp change, and that is really important. During a phase change, there is going to be no change in temperature. Instead, what's happening is, in this case, we're cooling down, the energy is being released as energy is, energy is being absorbed, and as energy is absorbed, because we're warming up, despite the blue color scheme I've picked, we are warming up. So as energy is absorbed, bonds, okay, and we'll put that in quotation marks, are broken. Now, the reason I'm putting bonds in quotation marks is because we're actually talking about intermolecular forces here. If you guys remember back, we talked about IMFs back when we were still meeting face-to-face. The intermolecular forces, they're going to be your dipole-dipole. They're going to be your London dispersion. And they're going to be your hydrogen bonds. Now, water, H2O, has all three of those. H2O is a polar molecule, so it has dipole-dipole. Everything has London dispersion forces, and because it has an H and it has O, remember hydrogen bonds are FON, F-O-N, so it has hydrogen bonds. So it has really, really strong intermolecular forces. But as you put in more and more energy, remember we're talking about a solid here, solid, it's very strong. But as you put more and more energy in, as you get it warmer and warmer and warmer, you're making it so it moves faster and faster and faster until finally the molecules can begin to break apart. And then you get a liquid, which is much more loosey-goosey. All right. So all that's going on. Now, let's keep going. Because after it becomes a liquid, the phase change is complete, and then it can continue increasing temperature. So as time goes on, we're going to see that temperature continue to increase. It gets warmer and warmer and warmer until our next important temperature, which is going to be 100 degrees Celsius. Now, in Fahrenheit, that would be 212 degrees Fahrenheit. But 100 degrees Celsius, this is science. We got to keep it all the same. And so nothing is really happening here. Okay, this is just liquid water. That's a G. This is liquid water. It's just liquid water that's getting warmer and warmer and warmer and warmer, okay, as it goes on that line. All right. So we start with a liquid. So up here, when we get to 100 degrees Celsius, it's still going to be a liquid. Right here, still going to be a liquid. Okay, that looks like a Hershey's Kiss. I'm trying to draw a water droplet, but you know what? We'll keep it. There you go. But at this point, when it reaches 100, it's going to undergo another phase change. So we see that line start to flatten. Now remember, if the line is flat, that just means that even though time is still increasing, guys, time marches ever forward. Okay, you can't stop time. It just keeps going, going, going. But the temperature is going to stay the same. Temperature is going to stay the same on that line. And it's because this is a phase change. So at the end of this phase change, then, we would expect to have water vapor, which is the gaseous form of water. Excuse me. Good morning. That's the stuff. I know you guys miss me chugging water and making it way too loud. All right, so during this phase change then, notice there is still no temperature change, no temp change, okay? But instead, this is where energy is still being absorbed and those bonds are broken. Intermolecular forces no longer have any sway. Because when you get it into the gaseous form, the water vapor molecules are so far apart. Okay, here's an H2O, here's an H2O way over here. Because the thing is, in solid, which as you guys know, ice floats in water, so technically solid water, okay, H2O molecules are this far apart. But when it becomes a liquid, they actually get a little bit closer together. They get a little more dense, but now they're loosey-goosey. But when it becomes a gas, they are so far apart that intermolecular forces don't matter anymore. And so that's why the bonds are fully broken. In fact, it would be better if instead of me saying bonds broken over here when it goes from solid to liquid, I really should say bonds are weakened. Because the bonds are still there. Those intermolecular forces are still there. They're just not very strong. So anyway, this is a warming up. All right, this is a warm-up curve. Because we can see you start with a very low temperature and you end at a very high temperature up here at the very top. And so we're dealing with two phase changes here. When you go from solid to liquid, well, hopefully you guys know that's melting, which annoyingly in chemistry, it's also called fusion. I don't know why. Morgan, why is melting called fusion?
That's just the energy it takes.
Yeah, but why do they call it fusion? Because it's getting weaker.
I would say because the...
Yeah, we don't know. We don't know. This is two chemistry teachers, and we just know that it's called fusion because we're going to talk about heat of fusion later on, which is basically how much energy do you have to take in to fully melt something. But nothing's getting fused. See, when you think of fusion, you might think of combining two things, like, ooh, calculator, case. Now they're fused together. But I don't know. That's what it's called. I don't know. Thanks. And then obviously when we're going from liquid to gas, this is going to be you would want to call it evaporation, but it's not evaporation in this case. This is actually boiling. We're talking about 100 degrees Celsius. But in general, it's called vaporization. Okay, vaporization, because that's the phase change meaning. Now, vaporization can either be evaporation, which occurs very slowly. It only occurs on the surface of something. So if you think about like a pool of water, you know, like our puddle, which is all over my construction site right now. There's puddles of water everywhere. Hopefully they're going to evaporate throughout the day. But evaporation only occurs at the surface. It only occurs at the surface. So only where air is making contact. But boiling is a forced phase change, and it occurs everywhere. When you're boiling something, okay, so we got a little pot right here. It's boiling all the way through. It's boiling all the way through. In fact, you see those bubbles form at the bottom, and then you get the steam out of the top. Okay, so anyway, that's a warm-up curve. The cool-down curve is going to be basically the same. I'm going to go a little bit faster this time, but it's going to be very similar. Okay, so let me erase some of this junk. Go away, go away. Here we go. So we're going to do a cool-down curve now. Okay, so we're gonna do the opposite. We just warmed up some water, and we're gonna cool it off. And we're gonna cool it off. There we go. That looks great. Now we're gonna start with our curve way up here at 100. We're gonna begin at 100, and in fact, we're gonna start above 100. I take that back. We're gonna start above 100. Maybe we've got some water vapor that's really hot. Maybe it's super warm. And I mean, you can do that. You can get water vapor and make it extra hot so that it's even warmer than 100 degrees Celsius or 212 degrees Fahrenheit. So let's just say that. So we start with a gas up here, and then we're going to cool it down until it reaches 100 degrees Celsius. Now, at 100 degrees Celsius right here, we're still a gas. Okay, we still have water vapor. But that phase change is going to occur. And remember, during a phase change, we see that line flatten out. And it's because during the phase change, it's going from a gas here, it's going into a liquid, okay? It's going into a liquid. And the reason we know there's a phase change, there's no temp change. No temp change. And instead, what we're looking at is an energy change. Now, because it's cooling down, it's not taking in energy anymore. It's now releasing energy. You've got to think. Those gas molecules are moving so fast. They have a lot of kinetic energy, which hopefully you guys know is the energy of motion. And so if they have all this kinetic energy, if we start to cool it down, these molecules are slow now. They have less kinetic energy. And as you guys know, energy is not created or destroyed. It is only transferred to other things. So as it's moving like this really fast, if it starts to cool off, that energy has gone somewhere. So energy is not being absorbed. Energy is released. Energy is released. Fantastic. There we go. And as energy is released, now we have bonds. And again, I'm putting bonds in quotation marks. We're really talking about intermolecular forces. In fact, I'll write it. IMFs, okay, are formed. Because as a gas, as I just told you, as a gas, they're so far apart that they really can't do anything. But when they get to be a liquid and they're really close together, now we've got a little bit of London dispersion forces. Oh, now we've got some dipole-dipole forces, only when they're close together. Okay. Yeah, Emily, I really hope so as well. Okay. I was so discouraged last time because there were not very many people that watched it. Yeah. So anyway, if they don't watch it live, which let's go check in. I'm prepared to be underwhelmed. We got 4 whole people watching. All right. I'm hoping they'll check in later. But anyway, so now we've got a liquid, and as it gets colder and colder and colder, it's just going to get colder and colder and colder. So the thing is, even down here, still a liquid. It's just a much colder liquid. Okay, it's just a much colder liquid. Then we're going to get to another straight line because, as you guys know, this is going to be another phase change as it goes from a liquid into a solid. Okay, so now it's going to be a solid way down here. And so here, as we can see, no temp change. Guys, if you don't get anything else from this little bit of notes that I'm throwing at you real quick, during a phase change, temperature does not change. Energy is either going away and the bonds are getting stronger, or energy is coming in to break those bonds apart. I'm going to say that again. During one of these situations, okay, energy is either coming in to break the bonds apart, or energy is going out as the bonds become stronger. Okay, so during a phase change, there's no temperature change. Okay, and so instead, energy is still being released. Energy is still being released. And so these bonds just get stronger. Okay, bonds get stronger. There we go. Fantastic. And then finally, when you have a solid, maybe it just gets colder and colder and colder and colder and colder. All right, so here we go. So way down here, still going to be a solid. It's just going to be a much colder solid. Okay, there you go. Alrighty, so let's identify what type of phase changes we're talking about here. When you're going from a gas to a liquid, hopefully you guys know from earth science, this is called condensation. Okay, you have water vapor in the air. In fact, I expect today to be rather humid because it rained all day yesterday. Even when a well truck was trying to drive to my house in the pouring rain and there was mud everywhere, it was a disaster. But lots of rain. So today's going to be really humid, and as that humid air, rises up, as it gets higher and higher in the atmosphere, it gets colder, and as it gets colder, eventually it can condense and become liquid, which becomes clouds, which could eventually become precipitation. So gas to liquid, condensation. Liquid to solid, hopefully you guys know this from elementary school. When water gets really cold, it freezes. Okay, don't overthink that. So this was just going to be freezing. No special names for that. Freezing is freezing. All right, freezing is freezing. There we go. Okay, there are a couple of other phase changes that you guys need to know as well. There are a couple of other phase changes, and I am going to do this a very specific way. Let's scroll down. This is actually a perfect segue into the Bellwork from yesterday. So here's our Bellwork for 4:23. For my timestamp purposes, what time am I at right now? We're at 18 minutes-ish. So 0, 0 to 18, and now we're at 18 to, I don't know. So the Bellwork from yesterday said basically, that's all right, we're going to go over the worksheet next. It's in my schedule. I told you guys to make a triangle diagram of the different phase changes. Excuse me. All right. So we're going to have solid up here. Why not? Down here, we're going to have a liquid. And over here, we're going to have a gas. All right. And we're going to label all these different phase changes. So we just did a couple. We just did condensation and freezing. We can go ahead and add those on here. And understand, energy is being released here. Energy is being released. All right, so let's call this one. Okay, gas liquid. Here we go. So here's condensation. Okay. And then we also have liquid to solid, which is going to be freezing. Okay, and if you guys took the notes, thank you very much. Thank you for that. Yeah, I hope people actually join. I thought about doing a remind, but I don't know. I could. All right, so we have freeze and we have condensation. Now, both of these I did in red for a reason. I'll talk more about that in a moment. The next two I'm going to do in blue, also for a reason. So we talked about in the last diagram, solid to liquid. Now remember, we're going to go ahead and call it melting, but we do know that it has another name. We're going to go ahead and call that fusion later on, but we're going to just call it melting for today. And then over here we have liquid to gas. And again, when you're talking about the phase change, I don't want you to call it boiling. I don't want you to call it evaporation. I want you to call it vaporization. Okay, so let's go ahead and call that vaporization over here. Alrighty. And then we got a couple more. As you can see, we're missing this on here. These are a little less well known. Yeah, you guys probably don't know what these are, but I'm going to teach them to you. Gas to solid. Let's go ahead and do gas to solid first. And I'm switching back to red for a certain reason. This is called deposition. Good example of deposition is where you go is a frost. Okay, frost on the grass. That is different than just regular freezing. In fact, if you've ever looked at frost out on the grass, as you can see, it forms those very fine crystals, and that's because it's going from water vapor in the air to solid ice directly. It doesn't go into a liquid first and then goes to solid. If that happened, you wouldn't have those really fine snowflakey type crystals. Ah, good gracious. We'll be right back. Okay, I do apologize. I hope that I muted the microphone in time. That was a guy telling me my cabinets are ready. Yay! All right, so anyway, what are we talking about? So we got deposition. Now I got to go from solid to gas. Anyway, frost, like I was saying. If it were going from gas to liquid to solid, like frost would, instead of being those really fine snowflakey crystals, it would be frozen water droplets, because dew, okay, D-E-W, is really just condensation that condenses on the grass, blades of grass. That's what happens in the summer, which you guys wouldn't know because you probably don't wake up early enough in the summer to see the dew on the grass. So slovenly. All right, over here. Ooh, I don't want to do that in red. I want to do this in blue, because when you're going from solid to gas, this is called sublimation. Because over here, that band Sublime, they have that one song that you probably know called Santeria. Yay, I'm so excited about my cabinets. But anyway, sublimation is dry ice. Okay, if you've ever bought dry ice, which according to Will Rathburn, shout out in the chat to Will Rathburn, told me that you have to be, I think, 18, 16, 18. You gotta be 18 to buy dry ice at Ingles. So, I don't know. It's probably because you can hurt yourself. Guys, do not play with dry ice. You could hurt yourself. So anyway, solid to gas, dry ice. If you don't know, dry ice like makes a fog. Yeah. Okay. So anyway, all right, we're good. Now you're probably saying, well, Mr. Nairn, why did you do these in these different colors? Why didn't you just do it all in black? So, because that would just be boring, black and white notes. Well, you guys know me. Because there's exothermic phase changes, and we also have endothermic phase changes. So we got exothermic, we got endothermic. Okie dokie. Okay. Yeah, you literally can get third-degree burns. In fact, it was a trend back in my middle school days, actually, where kids got their hands on some dry ice and they would try and see how long they could take it, like putting it on the back of their hand, because they were morons. All right, I did not participate because I'm not a moron. Even middle school Marin, not a moron. Exothermic. The reason I say exothermic is because heat is released. Heat is released. In fact, if we scroll back up, we can see, oh, look, energy is released here and here. And that's why, well, if it'll load, please don't start being stupid right now. There we go. And as we can see in both of those, heat is released. So that means these are exothermic phase changes. Now I know what you're going to say, but Mr. Aaron, it's getting colder the whole time, so how is it releasing heat? That would mean it'd be hot. I know that. In fact, I'll have a better example here in a second. But the thing is, it's releasing the heat so that the substance can get colder and colder and colder. Or rather, as the substance gets colder and colder, it releases that heat. All right? So heat is released. And a good way to think of this, remember, we were just talking about gases as moving like this, really, really crazy all over the place. All right? Gases that are moving like this have lots of kinetic energy. So the energy is in the molecules. But as they get colder, okay, and colder and colder, we can see the molecules are getting slower and slower and slower. And as they do that, that energy is going somewhere. And so the heat is being released. Oh, man, middle schoolers. That's why I didn't become a middle school teacher, guys. That's why. Well, that and they require constant babying. All right, everybody, we're going to walk to lunch now. Okay, we're all going to go on a bathroom break now. You know, ugh, terrible. So an endothermic, ooh, that's not what I want to write. Heat is absorbed, okay? So an endothermic heat is absorbed. All right, and in general, what we want to say is if heat is being released, generally molecules get slower. And over here in exothermic, we're going to say molecules get faster. Now here's the fun thing. Really good example of this is with a specific type of endothermic phase change, which is vaporization. Vaporization, specifically evaporation, which we can think about the pool. Maybe pools will be open this year. Who knows? But when you go to the pool, you jump in, you do your swimming. If you're middle school, probably you're peeing, let's be honest. And then when you get out of the pool, what happens? You instantly start to get cold. And so you go wrap up in the towel and try and dry off quickly. The thing is, wouldn't you eventually dry off if you didn't even grab a towel? You just got out, went and laid down on a chair and just chilled. You would eventually dry off because you're evaporating. But the thing is, evaporation is an endothermic phase change. And so it takes energy to get those liquid water droplets to go from being liquid into being a gas. It takes energy for that to happen. And where is it going to get that energy? Yeah, it can get it from the sun, but it's making direct contact with your body. So it's absorbing energy from your body. So you feel it as very, very cold because you're giving that heat energy to the water droplets so they can eventually evaporate. So evaporation, endothermic phase change. And so therefore it feels cold as it's happening. Okay, there you go. Pretty cool. A good way to remember these if you're having trouble between endothermic and exothermic is just a quick diagram. We're going to do solid, liquid, gas in this order. Understand that as you go this way, molecules are getting faster. Okay, molecules are getting faster as you go from solid to liquid to gas. And so you've got to think then, okay, the phase change. Maybe it's sublimation. Okay, if it's sublimation, that means you're going from here to here. And you've got to ask yourself a couple of questions. Okay. So if you're going from solid to gas, okay, obviously we know this is sublimation because I just told it to you. But think about what's happening to the molecules. If the molecules are getting faster, that means they're getting more kinetic energy. And if they're getting more kinetic energy, where's that kinetic energy coming? By the way, guys, the Bellwork stopped back here. So if you're saying, wait, do we have to do all this for the Bellwork? I don't think so. I can go check. I don't think you had to do that. Now I can't even remember. Was this yesterday? And identify each as endo or exo. Yeah, but I did that with colors. So I mean, if you did it with colors like I did, that's fine. But yeah, that was it. This was the Bellwork right here. So if that's what you did, good job. All right. Anyway, what are we talking about? So as molecules get faster, you get more kinetic energy. And so if they get more kinetic energy, where are they getting that energy from? They have to take it in. They have to take in energy. Okay. Did I get that right? Yeah. And so this one is actually going to be, haha, I fooled you. This is endothermic. Even though I wrote it in red, it's actually endothermic. Okay, and so another way to think about it, say we're going the other direction. Let's say I'm going from gas to liquid. Okay, let's say I'm going from gas to liquid. I'm going to do this one in blue just to trick you. So if I'm going from gas to liquid, think about what's happening with the molecules. They're not getting faster. Molecules get slower. Molecules are getting slower because they're going from gas, to slowing down into a liquid. And as they slow down, that means there's less kinetic energy. And so you've got to think, oh, well, where did all that energy go? It can't just disappear. That energy they had went out into the environment. So this is exothermic. It's actually exothermic the whole time. So that's just an easy way to try and help remember this. Now you could, don't get me wrong, you could memorize all this. You could. I wouldn't. I would rather understand the concept and understand it this way. So anyway, there you go. Alrighty, so far, I'm going to drink some water here in a second. We've talked about these phase diagrams, these phase curves, where you either are cooling off, like we see here, or you're warming up, like we had earlier. We've talked about the 6 different phase changes, and whether they're exothermic or endothermic. And I can't remember if I've taught you this or not yet, so I'll go ahead and write it down now. Another thing that's worth remembering is exothermic. Think about exo as energy exits, energy exits. And with endothermic, I want you to think about it as endo, okay? Energy enters is what some people say, but I'd rather think of it as energy comes in, okay? So endothermic, energy comes in, exothermic, energy exits. That's a really good way to think about these. Really good way to think about them. And then finally, I taught you that little thing. All right, let's talk about PT diagrams. Because the issue with these phase curves is that they're great. They've got temperature, they've got time on them, but one thing they don't consider is pressure. Question: can you boil water at a temperature other than 212 degrees Fahrenheit or 100 degrees Celsius? Can you boil water at a temperature other than that? And the answer is yes. In fact, maybe you do a lot of baking. If you do a lot of baking, you'll realize it says on some boxes, it'll say for higher elevations, usually it has to be above 3,000 feet. They say for higher elevations, change your baking time to this. And the reason they're doing that is that because as you go to higher elevations, you have less and less pressure. Think about it this way. Okay, so look, we're here on the Earth. All right. Ooh, I get to draw an Earth. There we go. Here's Earth. It's going to be so good. It's going to pop up in a second. There's Earth. I don't know. Here's America. Canada, who cares? Texas. There we go. There we go. That looks like America-ish. So, as you get further and further and further away from the surface of the Earth, there's less pressure because there's less air pushing down on you. I mean, if you're standing on the surface of the Earth, look at all this air pushing down on you versus the amount of air when you're at higher elevations. And so there's less pressure as you go higher and higher up. Okay, so question was, can you boil water at a temperature other than 100 degrees Celsius? And yes, you can. In fact, you can boil water at room temperature. You can do it. Let's see here. I want to go to YouTube, and I want to go to boiling water in a vacuum. There we go. Because I don't have my vacuum, so I'm going to cheat and do this. Here we go. Here we go. Some quality content here. So as you can see, they're at about 24 degrees Celsius. So 24 degrees Celsius, that's like 70 degrees Fahrenheit. So that's room temperature. They have a vacuum pump here. And this is the vacuum pump. And so what it's going to do is he's going to put this glass dome onto this water. And when he does that, it's going to suck out all the air, basically. It's going to take away the air pressure. Okay, let's fast forward. It's taking too long. Okay, there we go. He's sucking out all the air. And we can see the water shaking. That's because the vacuum pumps are actually pretty loud. It's like that's what it sounds like. I'm not going to do sound effects, don't worry. But as we can see, temperature's still the same. Temperature's staying constant, but the pressure is getting less and less and less the longer that vacuum pump is on. See, temperature's still the same. Oh no, here it happens. So as we can see, when you take out enough, you can see the little bubbles forming down here at the bottom. Oh, here it goes. Here it goes. It's going to do it. Oh, it did it. Boiling. Wow, science. And as we can see, the temperature never changed. So if you take away, okay, if you take away enough pressure, you can actually make that happen. And that's where PT diagrams come in. Glorious PT diagrams. So on a PT diagram, okay, give me a second. Do I have my next thing ready? Yeah. On a PT diagram, you're going to have pressure and temperature. So we got pressure over here. And just for consistency, we were talking about the atmosphere a second ago. One of the units for pressure is ATMs, which stands for atmosphere. If you're at sea level, guess how much pressure you have acting on you? 1 atmosphere's worth, because there's 1 atmosphere of air above you. Down here, we're going to put temperature, which is going to be measured in degrees Celsius, because it's science class. And so when you're looking at these PT diagrams, this is usually what they'll look like, something like this. Okay, and here's the thing. When you are over there in the top left, okay, when you're over in the top left, that's going to be solid. Let's see, do I want to do this? Yeah, I think I do. I do want to do that. So over here is going to be all the solid. Okay. In fact, I need a new pen. Hold on. This is very important. That's a poopy color. There we go. Pink. Yes. That's what I want. Move it over here. Okay. So over here, everything is solid. Everything is solid. Everywhere over on that side. There is a reason for this, I promise. There we go. Beautiful. Solid. Next, everything in that next little section is going to be a liquid. So everything over here is going to be a liquid. So I need this pen to go over here and make it all purty. There you go. I kind of wish my highlighter size was a little bit bigger, but I'm not going to change it right now. Come on, come on, come on. Faster, faster, faster. I know you guys are impatient. You're like, Mr. Aaron, please get to this PT diagram. I'm so interested. Yes, I'm here. I'm listening. I'm going to go check the timestamp real quick. Where are we at? 37. Now we're at 37 to, I don't know. All right. Yeah, I'm here. Do you have a question? And then now at the bottom, we're going to have gas. While I'm doing this very important thing. So what we were looking at a second ago is it was going from liquid water into a gas, but it stayed at the same temperature. So we've got to imagine then, let's say, I don't know, they were at what, 22, 23 degrees Celsius. So let's say we're right here at 23 degrees Celsius, and they boiled water. Man, this delay is killing me. Oh my goodness. Yes. I really wonder if Corona beer is ever going to recover from this pandemic. Thank you very much. I'm going to have to tell that. All right, so we got 23. It's going from a liquid to a gas. But it did that as pressure decreased. Because remember, they started at 1 atmosphere worth of pressure in that chemistry classroom, and then it became, it started boiling. And it went on this line right here. Started at a liquid at 1 atmosphere of pressure, right? 1 atmosphere of pressure. And then as they got less and less and less pressure, eventually it crossed that line. And when it did so, it boiled. So here's boiling. Now, this graph can be kind of confusing to some people because you're going to look at it and you're like, oh, this doesn't make any sense. You have to think about it because we're not just changing temperature anymore. Now, yeah, can you go from a liquid into a gas by changing temperature? Yes, you can. It happens over here. I'm going to pick green. Because if you start right here, and you go that way, all you're doing is increasing the temperature. I'm only moving along one axis, the temperature axis. So as you go from left to right, okay, as you go from left to right, we can see that you're increasing temperature. And so, yeah, this can also be boiling. So you can either boil from going left to right or going from up, up down. Hey, good morning, Tess. So boiling can happen in two directions, either by changing pressure or by changing temperature. And so now we're not just talking about changing temperature anymore. We're talking about all of it. All right, I'm going to hit undo a bunch of times so I can clean this up. Hope I don't do it too much. Uh-oh, that's all I can do. Okay, that's fine. I can make that work. Boom. So let's identify a couple of directions. Yeah, it's confusing. Let me show you kind of what's going on. All right, I'm going to talk about normal stuff first, just by changing temperature. Okay, just by changing temperature. So earlier we talked about going from solid to liquid, and we had a name for that phase change. So if you go from solid to liquid, let's say all of this is going to occur at 1 atmosphere. So I'm going to identify this right here. This is 1 atmosphere, right there. So everywhere on this line is 1 atmosphere. Okay, sorry for my terrible dash line. So if you go from solid to liquid, if you increase the temperature in this region right here, and yeah, that's going to be solid to liquid melting. So you can melt something by going in 1 atmosphere and going like that. So again, that's 1 atmosphere pressure. That's regular pressure. At a higher temperature, can you go from a liquid to a gas? Yes, right over here. Okay, right over here. You can go from a liquid to a gas when you cross that black line. Okay, and so that's going to be vaporization. That's going to be vaporization. Again, we have not changed the pressure. That line is flat, so I'm not going up or down on my y-axis, okay? Because you want to think of pressure, you want to call that a y-axis. There you go. I don't know why, but but that 1 atmosphere stays the same, so pressure staying constant. There's melting, there's vaporization. Can you go the other way? Yes, you can. We want to go the other direction. I'm going to click undo a bunch of times and hope that it's enough. If you want to go the other direction, you can absolutely do that. Say you start with a gas and you're cooling it off. Maybe you're going this way. If you're going this way, going from a gas, look, here's where we start. Here's where we end. I start in the gas area, in that yellow area. I end in the liquid area. Yeah, it's just going to be condensation. There's condensation. Over here, you're going from here to here, still staying at 1 atmosphere. I'm still staying on that 1 atmosphere line. But if you're going from there to there, look, we start as a liquid right here. We end as a solid right here. Well, that's just freezing, y'all. So there, you can see those different phase changes happening. Okay, you can see those different phase changes happening. So the thing is, depending on what line you cross, you're going to have different phase changes. And so what you need to consider is, okay, what phase change is happening? And you just got to think about it a little bit. So say I start way over here and I end way over here. Can that happen? Yes. If I go from here to here, I'm going to draw my arrow on there and I'm going to say, I'm starting as a gas, I'm going to a solid. Well, when that happens, gas to solid, notice the two things that are happening. I'm decreasing temperature because look, I'm going to the left. And I'm also increasing pressure. Okay, I'm doing two things at once. You will probably not have to do two things at once. I'm just doing this for the sake of an example. So it's doing two different things. I'm cooling it off, and I'm adding more pressure. And so as that happens, gas to solid, I taught it to you. This is going to be deposition is the phase change. That's the phase change. So every one of these lines then represents a place where it can be more than one phase at one time. Okay? Each of these represents more than one phase at the same time. And so, okay, so can I click? Yeah, how do I delete it? I click more than one. That'd be nice. Whoa, how do I do that? Go over here. Sorry, I'm cleaning up my workspace a little bit. Okay, I really not get? There we go. All right, there we go. I moved everything out of the way I didn't want. No, I'm going to erase it. What were we talking about? Oh, yeah. So everything on that line, everything on this line down here could be both a solid and a gas. And look, here's that double arrow we like, in equilibrium with one another. Everything on this line up here is going to be a solid and a liquid. They're going to be in equilibrium with one another. Everything on this line down here is going to be a liquid and a gas. Okay, and once again, they are going to be in equilibrium with one another. Now, remember I was telling you guys about my dad's super cold refrigerator that he keeps in his shop? Well, that's because technically, in a way, he kind of keeps that water in equilibrium. In fact, if you get some of the water bottles in the very back of the fridge, those are already frozen. You get the ones near the front, they're all still liquid. But again, if you shake them up a little bit or if you hit them against something, they will freeze instantly. And it's because they're right there at that equilibrium point. So you guys may be wondering, well, Mr. Nairn, if that can be a solid or liquid anywhere on that line, what happens right here? What happens right here in the very middle? Because at that point, couldn't it be a solid, a liquid, and a gas? Well, yes, it could. And that point is called the triple point. That point is called the triple point. All the phases can occur at the same time. Okay? There it is. I'll show you what that looks like. And luckily, you don't have to hear the audio. So as we can see, this is cyclohexane. They do have it with a vacuum pump. That's what this gray hose is. They're taking pressure away. All right, so they're trying to suck away some of the pressure. It's still at room temperature. They're reducing pressure. Same temperature. Oh, look, there it is. It's freezing. It's freezing. Oh, no, it's frozen, but it's still liquid at the bottom. And then in a second, you're going to see some bubbles because it's also boiling at the same time. Come on, boil cyclohexane. You can do it. There it is. So see, it's boiling, freezing, and liquid. There we go. That's it. Triple point. All at the same time. So it's boiling, freezing, and liquid. There you go at the same time. It's real crazy stuff. And so that's what triple point looks like. That's the triple point. Pretty nifty. Okay? All right. One other thing I think I'm supposed to teach you. I can't remember what it was. Shoot. What's that called when you get past the line between critical point? Thank you. So over here, on a lot of graphs, you'll see this line for the liquid and gas line stop. Okay, so like if I make this graph go a little bit further to the right, okay, I'm going to make it go a little bit further to the right. That line can keep going that direction. We don't know. We don't care. Temperature is going to continue to increase this way. But when you get to this point right here, which is called the critical point, you don't see a line anymore. You're not going to see a line anymore. Instead of it saying, oh yeah, these are going to be liquid and gas at the same time. No. When you get past the critical point, is it a liquid? Is it a gas? We don't know. It's both. It becomes something called a supercritical fluid. This is called a supercritical fluid. And so that's the point where it's kind of a liquid, it's kind of a gas. Well, Mr. Nairn, do you have a video to show us since you don't have any chemicals in front of you? Well, yes, I do. Yeah, you can't tell. And that's what you guys are going to see in the video. You can't really tell if it's a... Thank you. Thank you, second teacher. I'm not co-teaching anymore. All right, let's take a look at this. So that line is showing you where it's liquid CO2 down at the very bottom. Now up here above, you're going to be able to see gaseous CO2. Okay, so as temperature rises, the liquid CO2 evaporates and the fluid level is going to lower. Okay. We're at 32.4 degrees Celsius. You can see it in the back. We're at 33. It's getting warmer. It's getting warmer. But at a certain point, okay, when you reach that supercritical fluid state, it's going to be kind of difficult to tell the difference between liquid and gas. So here, it's kind of like a gas. It's kind of like a vapor, right? But look, now you got liquid down there at the bottom again. Very confusing. Very difficult to tell. Am I dealing with a liquid? Am I dealing with a gas? And here we go. This is finally it when they get it at supercritical point. See, kind of looks like a liquid down at the bottom. But as you get it to higher and higher and higher temperature, you're going to start to see that it starts to look more like a gas. See, now it's trying to bubble. Now it's trying to boil at the very bottom. And so it's that mixing point between the two. We don't need to know about turbidity. I'm not going to explain it. Just get you confused. So see, kind of a liquid, kind of a gas. And what were you trying to say that was important?
It's just, at that point, you're at a pressure so high, and temperature so high, you can't make it undergo a phase change. Total liquid.
Yeah. So when you get past that point, you can't, I don't know if you heard my wife, you probably did. But when you get past that point, you can't force it to be wholly liquid anymore or wholly a gas anymore. It's a mixing point between the two, which is what we're looking at right now. Very mesmerizing. So you're not going to have any more condensation or vaporization past that point. When you're at super high pressure and super high temperatures, you can't really get it to be either. All right, you can watch more of that on your own time. We got more work to do. All right, so finally, that's PT diagrams. That's everything you need to know about that. But now we are going to look at that activity real quick. Okay. Yeah, no, I'll probably get in trouble for that later. All right, so here we go. PT diagram, group activity. Yeah, if I had done this in real class, it would have been a little bit different, but we're not in real class right now. It says, circle the following substance. Your group has been assigned. Well, all of you have been assigned the same one, which was CO2. Okay, I gave you a graph for CO2. That's the one we're going to do. Use your one-to-one device to find an image, blah, 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 blah. Okay. And this was really important. Find a diagram where pressure is measured in atmospheres and the temperature is measured in degrees Celsius. We want it to be the same as the notes. That's what's important. So label each of the following. So we're going to label each area as either solid, liquid, or gas, because in an ideal world, you guys would have whiteboarded this. And so when you whiteboarded it, you would have actually drawn this out, and it would have been a lot better. But, we're doing the best we can with what we got. So you're going to label as solid, liquid, gas, triple point, critical point. That is the main things you need to be able to identify. And honestly, guys, the best way to remember is solid, liquid, gas, so that when you're doing your PT diagrams, you always have that weird, it's almost like I don't know, it's like a fork, because it starts as one line and then it comes up and it branches off, but it always goes solid, liquid, gas. It always goes in the same place. And we'll see that here in a moment. In the table below, list a temperature and pressure you could start from and end at to experience each of the phase changes for your substance. Don't worry, I'm going to help you. It's going to be great. And then we have a couple questions. So here's the diagram I gave you guys. Why is it being cut off? Let's see if I can fix that. I don't want it to be cut. Oh no, it's set as a background. Okay, we may just have to make do, but I don't want to. How do I? There we go. I'm going to move that down just a little bit. Orders. Bring the front right here, and now we can set the background. No, I said bring the front. All right. Well, we'll just use it right here. All right, it's gonna be fine. So anyway, here's our diagram, our PT diagram. As you can see, solid, liquid, gas, they're always in the same places. Okay, solid, liquid, gas. It's great. It's already labeled supercritical fluid way up there. So as you can see, the line becomes blurred between liquid and gas. Triple point, I'll go ahead and label on here so we have it. Triple point is where, again, everything connects together. That's where it could be a solid, liquid, or gas all at the same time. Very crazy stuff going on. Okay, so if we look back at the instructions, we're going to do one for melting, vaporization, sublimation, condensation, freezing, deposition. Now, I'm just going to pick one, freezing. Could I do freezing by going liquid to solid and just going like this? Yes, I could. Liquid to solid, because technically that's freezing. You start with a liquid. Oh, shoot. I got to fix that. You're right. I probably look ridiculous. Here's what I'm doing. Sorry, y'all. So if you go from liquid, that's why I like to do a live stream, so you guys can fix those mistakes. If you're going from liquid to solid, that's still technically freezing. Think about it. That's still technically freezing, but this makes it really hard on you because you're having to pick some weird temperature up here and pressure. See, I'm changing temp. I have an initial temperature and an initial pressure, and down in here I'm going to have a final temperature and a final pressure. But you're changing more than one thing, and it gets really confusing. So what I recommend is when you do each of these, you change just one thing at a time. And I'll show you what I mean. So let's go ahead and do melting first. So melting, as you guys know, is when you go from a solid to a liquid. And I'm going to go up here to this line, this 73.0, because that makes it really easy. Let me do orange. No, I'm not. I'm going to do this magenta. Ooh, magenta. I'm going to start using that number right there, because that's going to make it easy. Let's say, start right here. And I'm going to go to, I don't know, we're going to go over here. Solid to liquid. Okay, now you guys tell me, does that count as melting, going from there to there? Yes, it does. Okay, yes, it does. This is going to be our melting. But we need to put some numbers down in our table. So let's see what we got. Initial pressure. PI is pressure initial. Initial just means the starting pressure. It's going to be 73.0 atmospheres. Final pressure. Still 73.0 atmospheres. Do you guys see what I'm talking about there? See, I stay on that same dotted line, so I'm only changing the temperature. That makes it much easier for you. So I'm starting with initial pressure, final pressure, same thing. I'm still starting as a liquid. I'm still starting as a solid. I'm ending as a liquid, and so that still counts as melting. So that's what I'm going to do for that one. But I do have a different temperature. So my initial temperature was negative 78.5. See, look, follow that dotted line down. See, follow that dotted line down. Negative 78.5 is what I started as. Sorry, that has a unit, degrees Celsius. And I don't know. Let's say I end at negative 25. I can't tell because, see, I don't have a number down here to reference, but it doesn't matter. It'd be the same thing. So T final, negative 25.0 degrees Celsius. It's warming up. That has to happen in order for it to melt, and so that's going to count. So all I'm going to do now is I'm going to take those numbers and put them in my table. So melting, initial temperature, negative 78.5. I'm going to go ahead and put degrees Celsius right here, so I don't have to write it 1,000 times. Pressure, it's always going to be atmospheres. That's always going to be degrees Celsius. So there we go. That'll make my life a little easier. Initial pressure, I can see right here is 73.0. Final temperature, negative 25.0. Oops, let me write that. And final pressure, still 73.0. So see, I'm just putting everything in. And see, that counts as melting because look, I started as a solid and I went into a liquid. Easy, easy, easy. Now I'm going to do the same thing for vaporization, unless you guys have any questions before I keep moving. I'm going to give you a good 20 seconds to give me, how about this? Those of you, how many people we got on here now? Probably 5. Yep, I guessed right. So the 5 of you, give me 1 if you're really confused, 5 if this makes perfect sense. Go. Excuse me. I'm going to see what's going on Snapchat. Oh boy, somebody's eating tricks. And it's the good tricks, which is the one that has the shapes for the fruits. Oh no. All right. 4. I can take a 4. I can turn a 4 into a 5 in about 5 minutes. 3. Oh no. Well, I'm gonna try and get that up a little bit. Good morning, Caitlin. Glad to see you here. Anybody else want to respond? And drink a little more water, obnoxiously. All right. Well, I got a couple responses anyway. Let's see if we can get those numbers up. Let's do vaporization. In fact, I'll go ahead and write it down. We know that vaporization is going to be when you go from a liquid to a gas. So we've just got to find oh no, Emily, we're going to get it up. Vaporization, liquid to gas. Let's start with something easy, liquid to gas. I'm going to scroll down. I'm going to scroll down on here too. And I've got to start as a liquid. I've got to end as a gas. Okay, I've got to start as a liquid. I've got to end as a gas. I'm just going to pick a random spot, but remember, I'm going to try and keep my line either straight, look at my little camera, either straight like this or straight like this, either vertical or horizontal. I don't really want to do diagonal because that gets a little too confusing. So it's either going to be perfectly horizontal like the last one or perfectly vertical. In fact, let's go ahead and do, I don't know, we can do a vertical one this time. We can do a vertical one. What did I say we're doing? Was it vaporization? So liquid to gas. So I'm gonna pick right here, and I'm gonna go to right here. I can do that because look, I'm starting as a liquid. I'm going to become a gas. Okay, liquid to gas. All right. So now we just got to use the graph. Okay, we're looking for basically X and Y initial, and then X and Y final. All right. So what I'm gonna do is I'm gonna draw a line over to it. Okay, there. And I'm going to draw another line down to the next one. Okay, like that. And I'm also going to drop a line down. So what's staying constant here? What am I changing and what am I keeping the same? Please type in an answer. What's staying the same and what am I changing for this red arrow I just drew? I need to scroll up just a touch, don't I? That's better. Excuse me. What is staying the same and what am I changing? Look at the graph and tell me for that little red arrow, which this red arrow is going to represent vaporization. Anybody? Anybody want to type? Answer that question. Good answer. Yeah, temperature is going to stay constant. Pressure is going to be what's changing. Because as you can see, on the pressure line, I start up here, and then my second dotted line is down here. So I'm decreasing the pressure. Good job, Kevin. Good morning. Glad to see you on here. So pressure is changing. All right. So I'm just going to kind of have to make up some numbers because I don't really they don't give me a lot of numbers on here. Not super difficult. And so, I don't know. I know my temperature has to be something less than 31.1, so let's just make it 25. Okay, I'm just making up numbers. That's okay. That's acceptable. And then over here for pressure, I know it has to be less than 73 and more than 5. So let's just make this, let's make that 60. Let's make this, I don't know, 30. Okay, there we go. I'm just making up numbers. Yep. So that's 60 atmospheres to 30 atmospheres. So I can write it on here and say, all right, well, let's look at initial first. That initial just means starting. So I'm doing my starting dot. Right here. P initial is 60 atmospheres. P final is 30 atmospheres. Okay. My temperature initial is going to be 25 degrees Celsius. My temperature final, what do you know? Still 25 degrees Celsius. So as we can see, pressure is changing, temperature is staying the same. So now that we have that, I'm going to add it to my table very quickly. Initial temperature, TI, 25 degrees. I need to write that. And then final temperature, hey, what do you know? Still 25. Initial pressure, 60 atmospheres. Final pressure, 30 atmospheres. Okay, so there you go. I just updated my table. Okay, let's do, we can do sublimation. It's not that confusing when you are just using a PT diagram. So sublimation. As you guys know, sublimation is where you start as a solid and it becomes a gas. So we're going from solid to gas this time. We can do that. It's not a big deal. I'm going to erase some of my numbers down here on my table because it's looking a little cluttered. And we've used them. They were very helpful, but we don't really need them right now. Or we could still use it. Yeah, I'm still going to use some of it, but I'm erasing some of the clutter. Away. All right. Beautiful. All right, so let's scroll down. We're going from solid to a gas, solid to a gas. So I've just got to pick somewhere where that happens. I'm going to have to go way down here, way down here. I'm going to start right there. I'm going to end right there. Not a lot of choices when it comes to solid to gas. Sublimation has to have very specific circumstances to occur. So we're going, oops, yeah, that'll work, solid to gas. All right, so I'm going to draw my arrow because I'm going from a solid into a gas. So we're solid initially, we're going to be gas as our final. All right, so there we go. Everything's going to work out. And because I've already used some of these numbers before, this is actually going to be a little bit easier. Let me go ahead and label my arrow. This is going to be sublimation. There we go. I'm just going to say sublim. You guys know what it means. Alrighty. So as we can see, we have temperature that's staying constant. Pressure is what's changing. Okay, look. Temperature starts at TI 78.5 degrees Celsius. And then T final. Still going to be 78, negative. It's a negative 78, isn't it? 0.5 degrees Celsius. So we can see we're still on that same line. Yeah, it makes a lot more sense when I can actually explain it and draw all over it. That's why education in person is so much better. All right, and then we can see the pressure is changing. T initial is going to be 5.11 atmospheres. I know that because I'm just following the dotted line over. That's why I picked this spot, because I have some numbers I can use. And then when it comes to final pressure, we don't actually have a number. But we can make one up. It just has to be less than 1. So I don't know. We'll make it 0.5. Okay, we're going to make it 0.5 atmospheres. It's going to be great. All right, so I'm going to fill this information in my table real quick because, I'm just doing the same thing now. I'm just doing different phase changes and different points all over the graph. So let's see. Initial temperature, I had negative 78.5. And what do you know? Final temperature, still negative 78.5. Initial pressure is 5.11. And final pressure, 0.5. There you go. All right, here, I'll scroll up so you can see what I did. There you go. All right. Let's look at condensation then. Condensation. So condensation is going to be going from gas to liquid. All right, so condensation is going to be gas to liquid. Let me clean up my graph a little bit because it's not very pretty. I'm going to erase some of the junk I don't need anymore. In a moment. There we go. There we go. Ish. A little dot. Get that one little dot. It has to be perfect. You guys are worth it. So we're going from gas to liquid. So I got to find somewhere on this graph where I can start as a gas and I can end as a liquid. Now here's the thing. We have already done vaporization. Yikes. That's news to me, Ashley. Well, luckily you've had a lot of chemistry, so I hope that you can remember some of this stuff. Good, Emily. Let's get you to a 5. We're still working. We're going to get you to a 5. All right. So here's the thing, guys. Math online is going to be tough, Ashley. Good luck. So listen. We have already done liquid to gas. And so if we're doing condensation, that's just gas to liquid. So why would I not just do this right next to my vaporization line and just say, yeah, I'm going to flip it. I can do that. Now pretend like those lines, those arrows are on top of one another. I can't do that because otherwise it'd be a sloppy mess. But let's assume they're right on top of one another. I can do that. So this is now going to be condensation. Condensation. There you go. But now I'm starting as a gas right here where that dot is. Now I'm ending as a liquid right there where that ugly dot is. Let's do that again. So hey, it's going to work out. It's going to be fantastic. Gas to liquid. So I'm just going to use the same numbers. Initial pressure is going to be 30 atmospheres. Final pressure is going to be 60 atmospheres. Look, I'm just using the dotted line. I'm just using the dotted line and I'm following it across. Initial temperature is going to be 25 degrees Celsius. Final temperature, 25 degrees Celsius. Gee, what do you know? So it's the same numbers as before, just flipped. That's all. They're just flipped. So I'm going to write these numbers down. Initial temp, 25. Final temp, 25. Initial pressure, 30. Final pressure, 60. So as you can see, all I did is these two right here, kind of the same thing, it's just reversed. And that's okay. We can do that. And I'm going to do the same thing for freezing and deposition because now I can. So let's go look at freezing. I'm going to do the same thing. You guys know freezing is when you go from a liquid to a solid. Liquid to solid, excuse me. So let's do that. Let's find out where I'm going to do it. Liquid to solid. Here's liquid, here's solid. Hey, look, it's just melting in reverse. I can do that. So I'm going to draw another line that goes this way. Boop, there it is. And so this is now going to be freezing. There we go. That's now going to be freezing. Yay! Got you to a 5. But I am a completionist, so I'm going to do this quickly. So freezing is going from liquid to solid. Let's say, what was that initial temperature I picked? I can't remember. Melting. I said it ended at negative 25 was the number I made up. Okay, fine. So TI is going to be negative 25 degrees Celsius. TF is going to be 78.5 because I can follow that line down and see negative 78.5 down here. Okay. Pressure is going to stay constant because we can see pressure is 73 at the whole thing. So the whole thing. So P initial, 73.0 atmospheres. Remember, guys, at this point, every number should have a unit next to it. Don't be leaving any numbers naked. All right. P final, it's going to be also 73.0 ATM. Just like that. All right, so I got to go put those numbers on my chart. So I'm going to scroll up on my tablet. I'm going to copy these down real quick, and I'll be right back. Negative 25. Yeah, I'm sorry. Do you have something that you need to do? All right. Initial temperature, negative 25. And then final, negative 78.5. And pressure is 73 for both. Okay, so there we go. That's all I did. So as you can see, these two right here, same thing. It's just that I flipped it. I'm going the other direction. All right, and the last one's deposition. Deposition. Ooh, that was a bad voice crack. Wish I could edit that out, but I don't know how to do video editing, so I'm not going to be able to. So, deposition. So when you're going to go from a gas to a solid. So let's go do that. All right. And so for this one, I'm just going to flip my sublimation arrow, and I'm going to go the other way because I can. I'm going to go this way now. Way down there in the bottom because I can. And, yeah, I know, that was pretty bad. All right. What was my initial pressure? I can't remember. I'm going to use sublimation's final. It's 0.5. All right, so it's going to be 0.5. Why not? Okay, and my P final, I can see is 5.11 atmospheres because I can follow that dotted line over and find that. And we can see temperature is going to stay constant. T final, negative, 78.5 degrees Celsius. T initial, negative 78.5 degrees Celsius. So there you go. It's the same thing. All right, so I'm going to add these to my table, and then we'll answer these questions very quickly. And then we'll see what else we got to do. All right, so initial temp, negative 78.5. Final temp, negative 78.5, because the temperature stayed constant. All right. Pressure started at 0.5, and it ended at 5.11. Okay, so there we go. Table complete. Questions. Number 1, what is the temperature and pressure of the critical point of your substance? So remember, critical point, which is labeled actually, or it's going to be. Oh, no, I didn't label it. Remember, critical point is way out here, right here. See that over here? Right over here? Everybody see it? All right. So that's my critical point, and I didn't label it, and now I'm going to. Okay, so there's my critical point. And the critical point, luckily, they've given us those numbers. We just got to write them down in the blank. So 73 is the pressure. 31.1 is going to be my temperature. So 73.0 atmospheres. And what did I say? 31.1 degrees Celsius. There we go. There's question 1. Question 2, what is the temperature and pressure of the triple point of your substance? Well, it looks to me, I can scroll down and find it. I've already labeled triple point from earlier. It's going to be 5.11 atmospheres and negative 56.4 degrees Celsius. There you have it. Number 3. Now, these are important. This is really making sure that you guys understand what's going on. Okay? Oh, no, I didn't want to do that. I'm cleaning up my diagram real quick. Give me a second. Might need more than a second. Okay. At 1 atmosphere of pressure, if your substance is heated from negative 20 to 30, does a phase change occur? Okay, so I got to label that. I got to put that on my chart. Let's see. Let me use yellow. At 1 atmosphere of pressure, okay, here's 1 atmosphere. If your substance is heated from negative 20, that's probably like around here. That's probably negative 20 to 30. I know 30 is like right here. Does a phase change occur? Okay, so I've done some stuff. I'm going to go ahead and carry my 1 atmosphere dotted line over a little bit, and y'all can't see that at all. Let's switch colors. Okay, carrying all the way over here. And look, that's what I'm deciding is negative 20. It's an approximation because I don't have any numbers. Right here, I'm going to decide that's 30. Once again, it's an approximation. I know it's really close to 31.1, so I know it's got to be right around in there somewhere. So from negative 20 to 30, let's see. I start as a gas. I end as a gas. Does a phase change occur? No. No. It's a gas the whole time. Okay, number 4. At 0 degrees Celsius, okay, at 0 degrees Celsius, if your substance goes from a pressure of 0.5 to 200, what? Does a phase change occur? All right, so I got to find 0. I'm going to decide that this is 0 right in here. Sorry, this is so messy. Let's just decide this is 0 degrees Celsius right there. Okay, so somewhere on this dotted line, I'm going to have a question. All right, wow, that got really bad there at the end. Okay. And it says I'm going from 0.5 to 200. So I already know 0.5 is going to be like down here somewhere. So here's 0.5. I already know 200 is going to be up here somewhere where I can't see it. So I don't know. Let's just assume we're starting right there. Let's assume we're ending somewhere off the diagram, way, way up there. You guys tell me, did a phase change occur? Let's see. We started as a gas. We ended as a liquid. All right. So gas to liquid. Yeah, we know what that is. Okay. Gas to liquid. Yes. And this is going to be condensation. There we go. And I know that took a while. This is a pretty complicated it's a pretty complicated activity. But at this point, if you guys have any questions for me about this or anything else that you've been doing throughout the week, I would love to answer your questions while you're here. Thank you guys for tuning in. I hope it was helpful. Any questions you have, please ask them right now. And if nobody says anything after about 60 seconds, I will leave. Anyone? Or are you guys good? Okay. Have a good weekend, Kevin. Yeah, if you need anything, just send me a remind text or something. Anybody have any questions, or are we good? And by the way, this may look gross. That's just paint. That's the color of my house, y'all. See that? That's house color. Oh boy. What is this, a meeting? Yeah, I'm not going to that meeting. Nobody? Nobody has any questions? Okay, guys. I hope you all have an excellent weekend. If you do need anything, you know how to get in touch with me. I am here to help. As always, be proud to be a Jet. Goodbye.